I also talk about mixability, and that word mixable is a different thing on its own. Now, solution is simply an homogeneous mixture. There is a reason why we use the word homogeneous mixture, in which a solid dissolves in a solvent. Now, when you hear the word homogeneous mixture, are you getting me now? They are saying that only one substance is being dispersed. Are you getting me now? In that system. That's the meaning of an homogeneous mixture. Only one substance being dispersed in that system. Now, we said the solution is an homogeneous mixture in which a solute dissolves in a solvent. And when we hear the word a solute, we have to know the meaning of a solute and a solvent. Just imagine you are having milk and you have water and you put the water in a glass cup. Then you now introduce your milk into that water. That water there will later turn white because of the milk that you introduced. The milk is serving as your solute, while the water is serving to be your solvent. The milk is serving to be your solute, and the water is serving to be your solvent. So that's it. Automatically, in definition, we can say that a solvent, because it is the solvent that will dissolve that solid. The solid is the one that wants to get dissolved, while the solvent dissolves the solid. So we can say a solvent is the dispersing medium. When we say the dispersing medium, that's the medium to dissolve that solid. But on the other hand, a solute is the substance to be dispersed. So that's the meaning of a solution. So you are dissolving something in another thing, and that thing you are dissolving is called the solid, because that's what wants to get dispersed. Then the solvent, on the other hand, is referred to as your dispersed medium, because that's what will dissolve the solid. Okay, now solubility. When we hear the word solubility just simply refers to the amount of solute that dissolves in a given amount of solvent at a particular temperature. Now, the amount of solute that can dissolve in a given amount of solvent at a particular temperature, that's what we call solubility. That means what's the quantity of this substance the solvent can dissolve? What's the quantity of that solute that the solvent can dissolve at a given temperature? That's what we refer to as solubility. Okay, now we have different types of solution. We have what we call a supersaturated solution, we have what we call an unsaturated solution, and we have what we call a saturated solution. All these are depending on the solubility. They are depending on the solubility of that solvent. Let's look at this. We can say solvents. Sorry. There are three types of solution. We have the supersaturated solution, now your supersaturated solution is a solution that contains more number of solute than it can dissolve. It has more number of solute than it can dissolve. There is a level to which you add milk to water that the milk will stop dissolving. That's because it is now supersaturated. So there will be an excess of solute in that system. So we're having supersaturated solution to this. This is a solution which contains more number of solute than it can dissolve, at a given temperature. So that's what we mean by solubility. That's what we mean by solubility. Very, very easy. Then we can now, that's supersaturated solution. We can now look at our saturated solution, which is the second type. Now, when you say something is saturated, that means it contains as many solutes as it can dissolve. I get what I'm saying now. It's not containing more than it can dissolve, neither is it containing less than it can dissolve. Exactly the amount of solute it can dissolve at the particular temperature is what it contains. And that's when you say that that solution is what is saturated. So we say this is a solution. This is a solution. Let me highlight it. This is a solution that contains as much solute as it can dissolve at a given temperature. Very important for you to add at a given temperature because solubility is actually affected by temperature, also by pressure and concentration. So we'll be looking at those things and those effects in later lectures. So the last type is your unsaturated. Your unsaturated solution. When we say a solution is unsaturated, what do we mean? That means it contains a lesser amount of solute than it can dissolve. Let's recapitulate. These ones, the supersaturated contain more than it can dissolve. Saturated contains as much as it can dissolve, but unsaturated contains less amount of solute than it can dissolve. Less amount of solute than it can dissolve. This is a solution that contains less amount of solute than it can dissolve. At a given temperature. See that now? So that's what we mean by saturated, unsaturated, supersaturated. We've been able to define solvent and solute, and we've been able to talk about solution and solubility. Okay. Now we said that there are certain factors that affect solubility, and I'll be giving you some of those factors in a brief way before we start talking about them in depth. Now, one of them is temperature. Now, we must take note of the fact that at higher temperature, the solubility of a substance increases. And usually this is very, very common. If you want to dissolve, for example, now an amount of sodium chloride, and probably it's not dissolving quickly because of the amount of solute that was put into it, and you can actually increase the rate at which it gets dissolved by doing what? Or enable it to dissolve by increasing the temperature, heating it up. The moment you heat it up, automatically you see that it begins to dissolve. You get it? Then for pressure works in two ways. For a solid and liquid system. When you increase the pressure, solubility will what? Now, in fact, let's put it this way. Let me start for a gaseous system. In a gaseous system, for a gaseous solute, solubility. Now, how will you remember if it is increasing or decreasing? Just use this concept. Have you ever asked yourself a question why when you open a bottle of Coke, gases begin to come out, like you see this effervescent? That's because once you open the Coke, you reduce the pressure. And when that pressure is reduced, when the pressure is reduced, the gas molecules lose solubility and they begin to get liberated out of that solution. I get me now. So meaning that once you reduce pressure, because opening the Coke means you reduce the pressure inside. Once you reduce pressure, for a gas system, solubility it reduces. So decrease in pressure reduces solubility. Solubility is reduced by a decrease in pressure. Meaning that at higher pressure, you have high solubility. That's just what it means. Okay, we'll explain more of this in Henry's law when we're talking about Henry's law. You get, and because Henry's law is what explains these gaseous solubility processes. But I don't want to go into that immediately right now because I want to talk about phase diagrams. Phase diagrams, very important. You said in your syllabus, we're told to talk about phase diagrams. Naturally, we have three phases of matter, although there is a fourth one known as plasma, but we're going to be looking at three phases of matter: solid, liquid, and gas. Now, a phase diagram is a diagram that this is a diagram of the diagram of pressure on the y-axis plot against temperature on the y-axis and the x-axis rather. So now when you plot this, it tries to show you the phase changes that occurs under variations of this condition. This diagram illustrates phase changes that occurs, demonstrates phase changes that occurs at various condition of temperature and pressure. That's what we mean by phase change. Now I'll quickly draw or illustrate the phase diagram of, I'll quickly demonstrate the phase diagram of CO2, which is the typical phase diagram of CO2, and I will draw the phase diagram for water, and we'll be exploring those two. Now, the important point to be looking at in our phase diagram, we said phase diagram is drawn so we said on the y-axis we have pressure, and on the x-axis we have temperature. As we said, let me get colored marker here. Okay. Now, starting from this point here, I get it now. Starting from the point on your pressure axis, and let's say our pressure we're measuring it in ATM for clarity purpose, and our temperature here should be in Kelvin. Are we getting that now? Okay. Your phase diagram always goes in this direction. It always goes in this direction. You have starting from a particular pressure here, then to climb up. It now depends on what. Now this point where I stopped and is called the triple point. I will still explain to you. Each of these lines serves as a boundary of phase transition. It serves as a boundary of phase transition. When we mean phase transition, change in state is what we refer to as phase transition. Okay, so now this region here stands for our solid phase. There is our liquid phase, compressible liquid phase, and this other region here stands for our gas phase. Now this point right here is called the triple point rather. The triple point. Are you getting me now? It's called the triple point. Triple point. And why is it called triple point? Because that is the point where both the solid, liquid, and gas phase coexist. Are you getting me now? That's the phase point where solid, liquid, and gas phase coexist, and that's why it is called the triple point. Now, there is still another important point you must take note of here, and that's this point here from the gas phase. That's this point here from the gas phase. Which goes like this. And this point here is what we call the critical point. I'll be exploring the meaning of all these points now. Let me write this very well here. I want to give space to write my critical point, this gas. So we said this point is called the critical point. So if they ask you, they can give you a diagram now and they will draw, give you the range of temperature, they're asking you what temperature is the critical point, which you trace it down, and triple points there, that's where the three states of matter coexist. Now, this line here is serving as the boundary for what? When solid turns to liquid, that's called melting. So I can draw an arrow like this here, and that is melting up. This line stands for melting, and the reverse is called freezing transition line. So this is your melting and your freezing transition line. Why the other one here is why this one here is your gas, like turning from liquid to gas, that's your vaporization. Your vaporization, and when gas turns to liquid, that's condensation. Vaporization and condensation line. Very, very important. Your vaporization and condensation line. Why this point here? If you look at it here, when it turns directly from solid to gas, because the whole of this region here is gas. You get the solid, liquid, and the gas here. The whole of the region gas. That point where it turns from here to here is called your sublimation boundaries. I get it now, the sublimation and the deposition. You know, when a solid turns to liquid, when the solid turns directly to a gas, we call it sublimation. Sublimation. And when it turns from gas to solid, we call deposition. So I've been able to explain each of these lines to us. I get you now. I told you that they serve as different boundaries. I get you now. Now, what you must just know is that for the critical point, if this is the phase diagram for CO2, if this is the phase diagram for CO2, I get you now. Your critical point is usually at the critical point, triple point. Your critical point is usually at a given particular temperature of 31 degrees Celsius. 31 degrees Celsius. Let me use this one in Celsius. 31 degrees Celsius. I getting that now. 31 degrees Celsius and 73 atmosphere. That's very critical. That means normally if I should trace this graph was drawn to scale, by the time I trace this from here like this, I should be obtaining a pressure of 73 atmosphere. Again, normally this triple point is usually below, above your atmospheric pressure of 1 atm. That's one thing you must know. That's why the triple point usually have an atmosphere of 5.1 for CO2 now must have a pressure of 5.1 atm. I get now, but temperature of minus 57 degrees Celsius. And 57 degrees Celsius and 5.1 atmosphere. Those are important points you must take note of when you're talking about the phase diagram for CO2. Very, very important. Very, very important. So the critical point is where your liquid gas lines end. Because it's your liquid to gas line, that the line is end at the critical point. I get me now. Very, very important and very, very straightforward. Now, if you're drawing for water, this line, melting freezing line, actually is not positively sloped, rather it's negatively sloped. You get that now? It's negatively sloped. Okay, let me come back here now. We'll come back here. I think I'm about to wipe this off. I think we should write it quickly. Okay. So back here now. We've been able to talk about the critical point for water. Now I want to go to the critical point and for CO2. Now I want to look at the critical point for water. Very, very straightforward. The major difference between the two of them is that for the critical point of water, your boundary region for solid and liquid is the negative slope. indicator of difference. So if you have something like this, having pressure in atmosphere, and I have temperature, temperature in degrees Celsius. I have temperature in degrees Celsius. Now, all I will do now, the same way it was to come from here, the critical, your triple points, which serve as the boundaries between your solid and your gas state. So this line can also be referred. I'm repeating the just explanation of what before. This line that you see here can also be referred to as the what? As your boundary of sublimation and deposition. Your boundary of sublimation and deposition. Okay, so when you get to this critical point, if you were dealing with CO2, it will slope positively before you have your other boundary, which is your condensation and vaporization boundary. But since you are dealing with water, it slopes negatively. Then you now have your next boundaries. Good. Now, this one here refers to your solid, as usual, your liquid, compressible liquid, and your gas. Your solid, your compressible liquid, and your gas. Now, we know that from this gas phase here, we have another boundary, which is called your critical point is that point, or the end point, which is gas boundary. I get me now. That's point two. Any critical, your critical point and your triple point have its values. Your critical point and your triple point has its values. Now, for your critical point for water, you have it at 374 degrees Celsius and 218 atm. That's the temperature and the pressure of your critical point of water. But for your triple point, you have your triple point to be at 0.01 degrees Celsius and 0.006 atm. So this is an important point. So meaning that this point here is referred to as 0.01, and this point here, triple point pressure is referred to as 0.06 atm. I get it. Now, why this point here is referred to as 218 atm? Very, very easy to understand. So write that down quickly. That's what we'll be briefing in phase diagram. Now we're going to be looking at pressure effect on temperature. Okay, so I said before that I was going to be exploring. A bit of information on pressure effect on solubility. I'm going to be using Henry's law to do that. That pressure effect on the solubility of the gas. Pressure effect on the solubility of the gas. That's what I want to look at. Pressure effect on solubility of the gas. So what's the pressure effect on the solubility of a gas? I said we can use Henry's law to explain that. And what does this Henry's law state? That this can be explained using the Henry's law. And what does Henry's law state? It states that the solubility of a gas is directly proportional to the partial pressure. So that means when the partial pressure of that gas is high, the solubility of that gas will be high. You get it? The solubility of a gas is directly proportional to the partial pressure of that gas over solution. So I think I should write that down. It states that the solubility of a gas is directly proportional to the partial pressure let me see the solubility of the gas, that is how the gas dissolves. And when you say something directly proportional, the directly proportional is partial pressure, meaning that the solubility will be higher when the partial pressure is what? Is higher. So it's directly proportional to the partial pressure of the gas above the what? Above the solution. Above the solution. And it has its relationship. The whole of what I'm using here can be written in this format. Solubility is directly proportional to what? To partial pressure of the gas. Are you getting me now? Okay, this is partial pressure of the gas above the solution. So to remove proportionality sign, we know that we have to bring in a what? An equals to and a constant. And that constant is known as Henry's constant. So we are having S equals to KHP. When you remove this, because it equals to K. This KH together is your Henry's constant. Where KH is Henry's constant. So I'll just quickly solve two questions from this aspect and we'll move on. Two questions from this aspect and we'll move on. The first question says, at problem 1, says that the partial pressure of carbon dioxide of carbon dioxide to CO2, partial pressure of carbon dioxide gas inside a bottle of cooler, inside a bottle of cooler, inside a bottle of cooler is 4 atm at 25 degrees Celsius. 4 atm at 25 degrees Celsius. Then the question this is, what is the solubility of CO2? What is the solubility of CO2? Given that the Henry's law constant is 3.3 times 10 to the power minus 2. Given that pH for CO2 is 3.3 times 10 to the power minus 5. And of course, when you look at it, you should easily know because you should be able to classify the unit of pH from here. We know that solubility is that about number of moles of the distance of the solute dissolved in a given amount of solvent. I get me now. So you can easily identify that we're talking about mole per liter per ATM. Mole. So this is mole per liter. And when you divide it by pressure, you have it per ATM. So that's our problem 1. That's problem 1. So let's look at problem 2 that we'll be solving for today. I'll be rubbing this off so I can introduce our problem 2 here. So this next problem, problem 2, this is Henry's law. The question says that if air contains 75%, 78% N2 by volume, if air contains 78% of N2 by volume, right there, in water, okay, N2 by volume, what is the solubility of N2 in water at 25 degrees Celsius? What is the solubility of N2 in water at 25 degrees Celsius and 1 atm. That is the pressure, 1 atm. So we're giving the Henry's constant there. We're told that the KH for N2 in water, KH for N2 in water is equal to 7 times 10 to the power minus 4 mole per liter of atmosphere. So that's the question, that's the problem. That's the problem. So let's solve them together. Solution. Solution now. So we start with problem 1. Solution to problem 1. I believe you've written that problem 1 in your book. We have the partial pressure of carbon dioxide gas inside a bottle of cola is 4 atm. So we have been told that our P of that gas, which is CO2, is 4.0 atm given. All right, not the parameters. I get me now. Then I said at 25 degrees Celsius. What is the solubility of CO2? So I'm looking for the solubility of CO2. Given that KH, we're giving our KH is 3.3 and 10 to the power minus 5. mole per liter dot ATM. See that now? So we know that from our Henry's law formula, we said P is equals to S is equals to pH dot P of the gas. We know we wrote this down. So that means that we'll be having our S to be equals to KH, which is this 3.3 times 10 to the power minus 5 times 4. So when we punch that into the calculator, that will be giving us a value of 0.1 mole per liter. 0.1 mole per liter. I'm not making a mistake. Hold on. Mole per liter, yeah. So the question says use power minus 2. The question says use power minus 2. The question says use power minus 2, so you're having 0.1 mole per liter. So that gives us the answer for the solubility of that gas. So let's go to solution to problem 2. Problem 2. So problem 2 now. I believe we've written down the question for problem 2. It said if air contains 78% N2 by volume, what is the solubility? So we're still looking for solubility in this question. What is the solubility of N2 in water? So we're looking for N2 water solubility, and we're told our pressure, the partial pressure of that gas was equals to 1 atm, and our KH was equals to 7 times 10 to the power minus 4 mole per liter dot atm. You get that now? So we know our formula is S equals to KH dot P of the gas. So automatically our solubility will be equals to what's our K? 7 times 10 to the power minus 4 times our P, which is 1. And that gives us our solubility to be 7 times 10 minus power minus 4. And then multiply this together. Mole per liter. Very, very straightforward. Very, very, very straightforward. So if you need more questions, you can actually reach me and I will help you with more questions. So the next thing I want to be looking at is quantitative ways of expressing concentration. Quantitative ways of expressing concentration. Quantitative ways of expressing concentration. That's what we're looking at now. So you can express concentration in a variety of ways, in a number of ways. We have molarity, we have mole fraction, parts per million, parts per billion. Once we are done with this aspect, we'll be going to colligative properties. So I said we are going to quantitative ways of expressing concentration. Okay. We can express concentration in a number of ways. You can express concentration in terms of molarity. That's the first way. I'll be dividing it into tabular form. We look at the concentration term, then I'll also look at the ratio. I have concentration term, and I have the ratio. Let me say the ratio. I mean the formula for each of those parameters. I believe it's clear. So the first concentration term I'll be looking at here is molarity. And molarity is simply the amount of moles of solute over the volumes of the solvent. The amount of moles of solute over the volume of the solution rather. Number of moles, carried as moles of solute. Moles of solute over volume. This volume is in liters of solution. This solute. You see that now? Number of moles of solute over the volume of solution. That is your molarity. Then you have another one known as molarity. Do not confuse them. You have molarity and molarity. Now, molarity represented as small letter N. Now, molarity means the number of moles of solid over the kilogram of solvent. Number of moles of solid over the kilogram of solvent. So you're having mole of solute over kilogram of solvent. That is usually to be mole per kilogram, of course. Mole per kilogram. Why this one is mole per liters. So that's your molarity. The next one I'll talk about is part by mass. Part by mass. They can tell you to look for the part by mass of a substance. Part by mass. Like that's what you call PDN. And when you say part by mass, you're talking about the mass of solute over the mass of the solution. Mass of solute over the mass of over the mass of the solution. Then we look at the next one, which is going to be our parts by volume. Parts by volume. That's what you see as PBV. And that one just means the volume of solute all over the volume of the solution. So the solute is the one dissolving in the solvent, then the solution is always formed. Volume of solution. The next one you can hear things like part per million, part per billion, all those things are just any of these expression times that number. If it's per million times 1 million, if it is per billion times 1 billion, any of them. Okay, so I also have mole fraction, that's the last one. Which I represent as X. And mole fraction is simply the number of moles of the solute divided by the mole of the solution. That is mole fraction. But we can always remember that the mole of solution is the mole of the solvent plus the mole of the solid. That is mole of solid over mole of solution. And this mole of solution here can mean mole of solid plus mole of solvent. You get? That's what it can mean. Okay. So having written all these things, we can now pick some questions and solve them now. I'll be solving one from each aspect. We will write a number of problems now and we solve it. Start with problem 1. Problem 1 now says, and by this influence, it says, what is the molarity of a solution prepared by dissolving 32.0 gram of a solution prepared by dissolving 32.0 gram of CaCl2 and your calcium chloride in 271 gram of water. That is the problem 1. So problem 2. Problem 2 said find the concentration of calcium. Find the concentration of calcium in parts per million, ppm, parts per million in 3.50 gram pills that contains 40.5 milligrams of calcium. So that's the part A of the question. Then the part B of this question now says, the label on a 0.75 liter bottle the label on a 0.75 liter bottle of Italian Chianti. Bottle of Italian Chianti indicates 11.5% alcohol by volume. Sorry, by volume. How many liters of alcohol does the wine contain? How many liters of alcohol does the wine contain? Okay. Then the last question, part C. So that's like 3 questions in one. Says a sample of rubbing alcohol contains 1.2 grams of isopropyl. Contains 142 grams of isopropyl alcohol, which has the formula of C3H7 OH and 58 grams of water. Grams of water. What are the mole fraction of alcohol and water? What are the mole fractions of alcohol and water? Okay, these are the questions we are going to be solving. We are going to be solving these questions one after the other. Really important here. Solution to problem number 1. So what's the molarity? We are looking for molarity here. Of a solution prepared by dissolving 32.0 grams of this CaCl2 in 271 grams of H2O. In any question like this, first thing you have to do is identify which one is your solute and which one is your solvent. Now, they told you that dissolving CaCl2 in water, automatically I told you the substance that is dissolving is the solute. So CaCl2 is our solute and H2O is our water. So our solute here is what? CaCl2. Our solvent is what? H2O. The next step now, molarity. We know that in our molarity, what we need is, the formula for getting molarity is what? Is mole of solute over kilogram of what? Solvent. Mole of solute divided by kilogram of solvent. I believe you can remember that one. Okay, so that means what I need is to get how many mole of this solute is present and how many kilogram of this solvent is present. You get that now? So that's what I need. That's what I need. So this is prepared by dissolving 32 grams of CaCl2. 32 grams of this is present. So to convert this to mole, remember that mole is equal to mass all over molar mass. They call that mole is equal to mass all over molar mass. So that means our mole of the solid to be mass, which is 32 given to us there. Now, molar mass of calcium chloride, calcium is 40, so we're having 40 plus chlorine is 35.5. Then we're tightening it by 2 as this 2 here. You see that now? Okay, so that gives us that our mole of solid to be 32 all over. 35.5 times 2 gives us 71. Gives us 71, if I'm not mistaken. 71, then 71 plus 40 gives us 111 gram per mole. So when we divide that value there, probably let's put into our calculator. We should be having 0.288 mole. 0.288 mole. So our mole is equal to 0.288 mole. So that's the number of moles of our solid. They give us 32. We converted it to mole. That's this by using this formula mass over molar mass. But in the formula, they not say we should get mole of solvent. That formula is mole of solid over kilogram of solvent. They gave us in the question already the gram of our solvent. He said 271 gram of H2. So having 271 gram. We have to convert it to kilogram. So to convert this to kilogram, divide it by what? 1,000. And that gives us what? 271 all over 1,000 kilogram, which is equal to what? Which will be giving us 0.271 kilogram. Yes. So that's what it will be giving us. So having done that now, we just slot it into our formula here. We're saying that thus molarity, which we said is equal to mole of solid, and our mole of solid is 0.288 moles over kilogram of solvent, which we got as 0.271. Okay, they give us that solvent in gram, but we have to convert it to kilogram and divide by 1,000. So when you divide this, it gives us what value? It gives us the value of 1.06 molarity. 1.06. You can write the unit like this, small letter m, saying that it's molarity. I get you now. You can write it like that. Molarity of CaCl2. So you can write it this way. 1.06 molarity of this, or you see 1.06 mole per kilogram. That is following the unit convention, mole per kilogram of CaCl2. Anyway, you leave the answer is correct. Okay, let's solve problem number 2. Let's solve problem number 2. I'll be wiping off this side now. I'll be wiping off that side. solve that problem number 2. So once I do problem number 2, the next aspect of this topic is your colligative properties. The solution to problem 2. Okay, problem 2, I believe you wrote that question down, so you can just read it from your note there. Problem 2 says, find the concentration in parts per million. I'm looking for concentration for the part A, come in parts per million. That's what I'm looking for. Of calcium in 3.5 gram pills. So now, that pills, I get it now, is the solution because so many things came together to form the pills. So we are saying that your pills, the mass of solution was given to us, mass of solution, and they said it was 3.50 gram. And they said it contains 40.5 milligrams of calcium. Mass of calcium that was dissolved in that pill was 40.5 milligrams. 40.5 milligrams. And they want us to calculate the parts per million. They want us to calculate the parts per million. To do that is very, very easy. Since they are giving us our quantities in terms of mass, all we will just do here, is to make use of our parts by mass in relation to per million. So remember that, we know that means conc in parts per million will just be equal to mass of calcium all over mass, I give you that, of solution, which is the pills, times, since they said per million, say times 1 million. Very, very easy. So who can write that as 10 raised to the power of 6? So in slotting these values into what we have here, they are having mass of the calcium, which is like the mass of the solutes. Okay, that's what it's doing. 40.5 milligram. Converting that, milligram is divided by 1,000, and that will be giving us 0.0405 gram. Okay, so we're having 0.0405 gram divided by mass of solution here is 3.50 gram times 1 million, which is 10 to the power of 6. So when we punch that into the calculator, we have the value of 1.16 times 10 to the power of 4. 1.16 times 10 to the power of 4 parts per million of Ca. So that means this is the amount of Ca that will be present in 1 million of that amount of pills. That's just the meaning. So the basic thing you must take note of is all those relationships we wrote here. All these relationships. See that? What we just applied here was our part by mass. Why did I use the part by mass? Because everything they were giving to me was in mass. That was the reason why I used the part by mass. They gave me everything in mass. They're giving me mass. So for me to be able to obtain the part per million and using the mass unit, I have to use parts by mass and multiply it by 1 million. That's giving me my answer in part per million. So calcium there was used in making the drug. So that means calcium is present or dissolved in that drug, in that pills. Are you getting me now? So that's why we have calcium as part of the solid, as calcium as the solid, and the whole pills is the solution. Do you get that now? So let's look at part B of that same question. Let's look at part B of that same question. I believe you wrote it down. So part B says The label on is 0.75 liters of Italian Chianti indicates 11.5% of alcohol. Now, they have given us our percentage of alcohol. Alcohol was part of the thing is making this thing. They said the percentage of alcohol was 11.5%. Are you getting me now? And the volume of this bottle of Italian Chianti was 0.75. That means that's the volume of the whole solution. Because the Chianti is like the drink that contains both the alcoholic content and your normal blends. So we are having 0.75. So it's just the ability to identify which one is the solution we're going to see. So now said, how many liters of alcohol does the wine contain? How many liters of alcohol does the wine contain? That's what the question is. Now, we will say volume. We don't know the volume of the alcohol. And this volume of alcohol is what we're looking for. And the alcohol is part of the drink. This solution is like the drink. The alcohol is a part of the drink. So we are saying the volume, we'll be using our part by volume. Volume of alcohol. I get it now. All over the volume of the whole drink, which is the solution. The alcohol is like the solid. Times 100 is equals to 11.5. That's the meaning of that statement there. That's the meaning. Because normally, volume of alcohol over this times 100 will give us our percentage of alcohol. But they've given us our answer of percentage of alcohol, so we put these values and obtain the volume of alcohol there. You get? So that means I'm saying volume of alcohol all over volume of the solution, which is 0.75 times 100 is equal to 11.5. So what do we now do next? You cross multiply. You have written that to cross multiply, or I can just say that means 100, multiplying this numerator, 100 volume of the alcohol divided by 0.75 is equals to 100 is equals to 11.5 rather. So when I cross multiply, I'll be having 100 volume of the alcohol equals to 11.5 times 0.75. So I'm looking for the volume of alcohol, dividing both sides by 100. So the volume of alcohol will be equals to, when you punch this in your calculator, this time this divided by 100, that will be giving us the value of 0.0862 liters. 0.0862 liters. So that's what you'll be having. That's what you'll be having. Then finally, part C. A sample of rubbing alcohol contains 142 grams of isopropyl. Meaning that in that alcohol, you're having 142 grams of isopropyl. Are you getting me now? So I say, since they say gram, that's the mass of isopropyl, 142. Listen carefully to that question. A sample of rubbing alcohol contains. That means the whole of that alcohol is containing, I get it now, 1.2 grams of isopropyl alcohol. And they gave us the formula of isopropyl, C3H7OH. I get that now. And 58 grams of water. Mass of water. 58 grams of water. And that's what are the mole fractions of alcohol and water? What are the mole fractions of alcohol and water? I remember I've taught you guys mole fractions before. Mole mole fraction can simply be said to be the amount of substance in mole over total amount of solution in mole. And I've said that before. So to get the mole fraction of isopropyl, that means before we can start getting mole fraction, we have to get the mole of each of them. So what will be the mole of isopropyl using your mass over molar mass? That will be mass, which is 142, all over molar mass, which will be giving us carbon is 12, so 12 times 3 will give us 36, plus 1, hydrogen is 1, atomic mass 1 times 7 is 7, oxygen is 16, and hydrogen is 1. So we're having 142 over. When you sum all this up, what will you give us? 36 plus 7, that's for 3. For 3 plus 16, that gives you 69. Sorry, 59. 59 plus 1 gives you 60. We have it divided by 60, and that will be giving us the value of how many? That will be giving us the value of 2.36 mole. 2.36. 2.36 mole. So that's the mole of isopropyl. So what about the mole? Because we need the mole of both of them to get the mole fraction. What about the mole of the water? Note what that water is H2O. That's mass, which is 58, over molar mass of water, which is 18. That's H2O. You understand when you say H2O? H is 2 times 1, 2, plus oxygen, which is 16. That's 18. So when you divide 58 by 18, it gives us the value of 3.22 mole. 3.22 mole. 3.22 mole. Okay, so what will be the mole fraction? The mole fraction of isopropyl. I've done that in Dalton's law of partial pressure. That will be the mole of isopropyl over the total number of moles of the mixture. So I have the mole of isopropyl 2.36 divided by total number of moles, that is mole of isopropyl plus mole of water, that's 2.36 plus 3.22. That will give us the mole fraction of isopropyl, and that will be giving us the value of 0.423, 0.423, 0.423. But when we get the mole fraction of water, that will be the mole of water, which is 3.22, over the sum of the moles also, that's the total number of moles, 2.36 plus 3.22. And that will be giving us a value of 0.577. That's the mole fraction of water. That's the mole fraction of water. Now, we said already earlier, one thing you must take note of is that the sum of the mole fraction of all the constituents in that mixture must always be equal to 1. By the time you confirm this, when you add the mole fraction of the isopropyl and water together, it will give you 1. 0.423 plus 0.577 is equals to a value of 1. So, what we're doing right now, we're going to be coming to the end of this section of this lecture, and the part 2 of this lecture, we're talking about qualitative properties. I get you now. Where we'll be looking at vapor pressure reduction, we'll be looking at the elevation of boiling points, we'll be looking at the impression of freezing points, then we'll be looking at your osmotic pressure. Then we will now explore the role of this information effect on our phase diagram. We'll be looking at how it affects the phase diagram for different kinds of constituents. We'll be using water as a case study. So that's for that. Please feel free to ask questions. I get me now. Feel free to ask questions on anything you don't understand. I can actually do a video on the solution to your question. I get me now. It doesn't matter at all. Once you ask a question and I compile all the questions together, I'll do a video where I answer all the questions. All right. So that's that for this section. More questions will be coming up. I'll be giving you more questions. Digest all this that has been done and make sure you build your expertise so that you can be able to attain very, very high. So good luck on your studies. Wish you all the best in your forthcoming exam.